All right, welcome to 601 Statistics. I just went over a little bit of the syllabus before I started the tape, so if you're joining now, you'll still get everything you need to understand logistically what's going to happen in the class. And that's what I will do at this point. So let's go back to class 1. So we've got the date, I'm on page 3, class 1, we've got the date, of course, we've got the topics we'll discover, and in the far right-hand corner, we've got assignments. I recommend you take a look at these assignments before class if possible, just to start thinking about these terms and be in a better position to absorb the material. I've just got a list of everything I suggest you do with that material. Practice exercises that will be related to the concepts we go over in class. Sections I suggest you read to prepare that material. So for the first class, I've got work these chapter exercises, read this, work this, read this, work this, read this, work this, okay. And then number 8 is Excel exercises. So I've got some recommended homework you do just for the exercises, just to be ready to understand the material. And then I've got Excel exercises that I think will be useful for a number of reasons. 1, it's a chance to practice this material. 2, it's also a chance to use it in a format that could potentially be much more useful to you in a business environment. So if you're going to do some statistical analyses at work, if you're going to show your manager something, and you're able to do this fluently on Excel, then I think that's going to help you make use of the material. Alright, so I've got some Excel exercises for each class that I will ask you to do and turn in. So the homework problems where it says work these exercises, that's just optional. Get ready for the quiz and get ready for the exam. The Excel exercises are something which you'll actually turn in. You will find the materials you need to do the exercises on Blackboard. Everything's under course material. There will be a folder, I believe it's called Excel Sheet Data, and it will be a blank, not a blank, but a filled out Excel sheet where you can complete these exercises. So you'll look in your book, see what it's asking you to do, you'll open up the template that I've provided, and you'll say, oh, professor wants me to figure out how to do the normal distribution of 60% in that particular cell. Let me play around with that formula. Okay, good, got that one, go on to the next one. And you'll complete that sheet, and then you will submit that over Blackboard each week. Does that make sense?
I have a question.
Yes?
Where can you get help for Excel? I can do all this stuff on paper.
Okay.
I'm not good with Excel.
Okay, I can help you a little bit. Your classmates might be a good resource. I don't know, is there an Excel tutoring at Mercy? I don't
Pretty
think
much the
so.
only answer I've ever gotten is, oh, play with it and you'll figure it out. It doesn't work.
Okay, yeah, that's the answer I got.
But the YouTube tutorial is really good.
Really?
Yeah.
Okay.
That's
a good.
that's the answer I got in business school, and I became a convert of play with it and you'll figure it out. What's your name, by the way?
Vidal.
Miguel. All right, so I will definitely do what I can to help you. There are some good tutorial options, but I am somewhat of a fan of playing with it and figuring it out. Primarily because I went through so much pain and suffering myself. I want you to share in that pain and
I'd
suffering.
rather not.
And once you do, you realize that there's no necessarily any right answer. Because one thing you will encounter is when you read the textbook for the Excel exercises, it will, in theory, step you through each and everything you need to do. So that's the good news. So if we go, example Excel exercise. So this is the Excel exercise for chapter 2. And it literally says, enter your data in the column on the worksheet, select the cell in the worksheet near the data you entered, click on the formulas tab in the Excel ribbon at the top, click on the FX insert function in the far left to select the proper function categories, blah, blah, blah. It literally goes through.
Excel for dummies?
Well, it just like tells you what to do.
Okay.
The problem you're going to run into is if your version is slightly different than this version.
What version is in the book?
I don't know. But that, and then there, hey, how you doing, folks? So,
Okay,
So that's gonna require a little bit of playing and figuring it out.
Well, if I can't do it on Excel, can I at least do it on paper and submit that and then backtrack to the Excel?
Yeah? Wait a minute. Oh, okay, wait, do it in the back, just a minute.
Well, if I can't get a handle on it, on the Excel spreadsheet, I can do this stuff, you know, on regular paper.
Yes, do it on regular paper.
I can do the calculations
Okay,
and then submit it.
and then submit it on, well, see, that's the whole thing, is that you'll know how to do these, you'll know how to actually do the problem by doing the homework.
Right?
But Excel, the purpose of doing the Excel is so that you can do the exact same thing you just learned how to do on paper on Excel.
Oh, I got you.
Yeah. So, yeah, so we'll figure it out.
Okay,
I'm a little bit lenient on the timing of the Excel worksheets. You can turn those in late if you need to.
yeah, I'll make sure I get the work done, but I'll shoot you an email if I'm drowning.
Okay.
The textbook,
Yes,
which one, because I've been seeing different ones,
you've been seeing what?
different versions, I wasn't sure which one.
Yes, same here.
Can I take a picture?
Yes.
The blue one, okay. Can you tell me what edition is that?
This is annotated instructors.
There's a loose leaf, there's a loose leaf, yeah. I didn't know if that was.
Yeah, the loose leaf, do you want this? Yeah, I think the loose leaf seems to work well. Here's one. Oh, what does that say? Is it annotated instructors version? Okay, that's fine. Yeah, get that one. You could.
What does it say, that one?
Annotated instructions version.
So, has anyone looked, like, you had the syllabus information and you looked online and there was confusion as a result of that?
It's just different editions that are online.
Different editions,
Like
like
this
there's,
is like, I think the 13th edition, there's other editions that they're selling.
like the 12th edition,
Yeah,
11th
exactly.
edition? Okay, are they all, but that's 2014, right?
Yeah.
Yeah, so are there different 2014 editions?
No,
Okay.
there's older versions of,
Yes, so you want the 2004, the binder version is good, it's the exact same thing, it's just loose leaf. Thank you. So, you want the 2014 edition. If you already have an older edition, I guess we got this question a couple of times. If you don't have it, I would suggest you buy the 2014 edition. If you already have an older edition, you could try a strategy where you make friends with someone in class and compare your edition to their edition to make sure that you have the right information, and where you don't, copy off of your friend. That is a strategy you could potentially use, but I think it would be easier to have the 2014 version. Okay. So who needs a syllabus and class slides? You need a syllabus?
We were interpreting.
Yeah, you can sit down. Alright, everyone's got syllabus class slides. Okay. So you'll have homework problems, which are suggested, you'll have Excel problems, which you'll turn in. The other thing you'll do each week is a quiz. A quiz on the material from the previous week will be due the following week. You will take that on Blackboard. It will be a 1-hour timed quiz. It will be 2, 3, 4, 5, 10 questions, just covering the material that we went over in the previous week. If you do the homework problems, you should be in good shape for the quiz. At the same time, sometimes students get a little scared or frustrated by the quiz questions because it's the first time you're encountering the material in the test environment, it's timed, and also maybe you rush through the homework. So do your best, but what I will tell students who get frustrated with that is that the quizzes will just be warm-up for the exam. So the material and the questions that are on the quizzes, you will see very similar questions on the final exam. So use the quizzes as an opportunity to ingrain the material and ultimately prepare for the exam.
And the quizzes do what, before class, the next class?
Yes. So the material we'll go over tonight, there'll be a quiz which you will take on Blackboard. Please complete that before you come to class next week. Because we actually will sometimes just go over the answers in class, so I ask that you do complete it. Question?
The quizzes, after we complete them, will we be able to go back over them?
Yes, you will. You will immediately see all the questions with the correct answers. And the way that you go back over them is you click on My Grades, then you click on the quiz. It'll be, class quiz number 2, class quiz number 3. And then you'll click on the score that you got. And then you'll see all the answers.
So is it multiple choice or
It's
fill in the
There are a
blank?
couple multiple choice, mostly it's short answer. It's just, find the proportion, confidence interval. And you'll do the calculations and you'll write it
Are
in
they
there.
graded like Khan Academy, is it like to the 10th or the 100th?
No, I grade all of them. I'll go through and compare the answer. And you'll see not only the answer, but you'll see the actual work. I've gone through for every quiz question and spelled out the work and spelled out how it's done. Yes,
Will there be extra credit?
there will not be extra credit, but the way the grading breaks down, you'll have 8 Excel worksheets, which are worth 5 points each. You have 8 quizzes, which are worth 5 points each. So that's a total of 40 points for the Excel worksheets, 40 points for the quizzes, and then the final exam will be worth 40 points. So they'll each be worth a third of your grade. So the Excel worksheets, if you turn them in, make a good effort, you're gonna get 5 out of 5, you're gonna get 40 out of 40 for that. That's easy, and like I mentioned, a little lenient if you need extra time. Alright, so that's 1/3 of your grade, 100% right there, as long as you put in the effort. The quizzes, as I mentioned, sometimes students struggle and they get a little scared, but as long as you know the material and are able to do those calculations on the final, you can count that third of your grade as a strong percentage. So you'll have 100% on the Excel if you just even try. You'll have a good grade on the final as long as you know the material. And maybe if you struggle a little bit on the quizzes, I wouldn't worry too much about that. Make sense? Okay. So I think that's mostly important stuff. On page 5 of the syllabus, we've got the grading policy, just the normal range. On the bottom of page 5, we've got the assignments and point value. As I mentioned, the quizzes, each worth 5 points. Excel worksheets worth 5 points. And the final exam, the end of the semester, worth 40 points, total 1/4 of your grade. 1/3 of your grade, excuse me. Okay, so let's go back to the first page, attendance policy, plagiarism and cheating policy. Attendance policy, I don't take attendance. I hope you get something out of my class. I hope you want to come to class. So I'll try to monitor it that way. If you can't make it, like I mentioned, I will record the classes and there'll be a link to that on Blackboard. So if you can't make it and just need to know the material, you can watch the video. Or if there's places you had questions on, you can watch the video for that as well. Plagiarism and cheating. Yeah, I just want to mention there is a lot of trust involved with doing a class that has all the quizzes, and you'll actually have the final exam online as well. So 100% of your testing will be online. Please do not cheat. I'd like to ask you to do that, number 1. I don't say this to scare anyone, I really just say it to impress you, to show you how much work I've done on Blackboard. For the final, I actually went through the extremely painful process of creating individual exams, 20 individual exams. So you will have a unique exam for the final. And so if you trade answers with someone, I will not only know that you traded answers, but also who did it. So I wanted to just maintain some integrity of the final exam for sure, that way. The quizzes, if I get motivated, I might do that for 1 or 2 of the quizzes, but the quizzes, I'll just have to say, it's your chance to learn, it's your chance to get something out of the material, so please do not share answers with other students. Okay. Yes?
I understand that we are able to get, say, Microsoft Word, Office, and its other counterparts for free. Do you know how to go about doing that? Because my free trial expired on my laptop, so in order to.
Oh,
do that-
okay, so your question is, as Mercy students, you have access to free Microsoft Word?
Right, like actually be able to download, yeah, Microsoft Office to
I
download.
actually do not know the answer to that. I would direct you to IT, and I can give you their number after class. And if that doesn't work, you can ask me, you can email me or ask me again, and I'll direct you to someone else. Okay. So, let's see. I think that is it. Any questions on the structure? Yes.
You said we need a calculator, the one on our phone fine,
What's that?
the one on the phone is fine, calculator? Or,
Yeah, I don't know. What do you think, Lisa? Do you think students in my class are successful with a phone calculator?
in 507 they weren't,
They were not.
no.
Okay, so. So I
There's
know
like
one-
weird functions that you have to put in that the phone doesn't calculate, yeah.
Some people try it, but I think it might be a little bit difficult. You can turn the phone sideways and you can technically do it, but you might be better off spending $10 to $15 and just getting, you don't need a graphing calculator, you don't need one like, yeah, you don't need one like that, but you need, you will need exponent functions such as 5 to the third is 125. You will need factorial function, which is that exclamation point. You would need square root functions. Those I think are the only ones I can think of. Alright, the phone has it. Alright. Yeah. Okay, so let's get started then with the material for tonight. I'm having some trouble with the computer, so I will do this for at least the first half of class. I'll walk through the slides, and I will do calculations on the board.
Almost there.
Okay. I can do this.
All right.
Okay, alright. I'm afraid to keep pulling. So then it's like done. Oh, okay, there we go. Okay.
Right.
Alright, so I'm just gonna walk through the slides then, and maybe we'll take a break and I'll get the computer working, and we can do this over the projector. So the main thing, so if you look, I'm on page 1, class 1, the outline. The main thing we're gonna talk about tonight is the normal probability distribution, a fundamental thing of statistics. I've got a process where I'm gonna teach you how to calculate the normal distribution. In order to do that, I need to teach you combinations, I need to teach you the multiplication rule of probability, and then we will warm up with the binomial probability distribution. And then we will look at that and we'll say, wow, look what we've created. We've actually created the normal distribution. What does that tell us? That tells us a lot. And one way that we're able to use the normal distribution is by using z-scores. Z-scores standardize what's on the normal distribution that allow us to put any distribution of data in a standardized format. And then we'll talk about measures of central tendency, measures of dispersion. This is mean, median, and mode, and standard deviation. Some basic intro stats stuff. So, we're going to concentrate on for the next 40 minutes or so is the normal distribution. And I'm going to start by teaching you combinations. So let's do that on page 2. Combinations. So this is a counting mechanism. I'm gonna pose the question, suppose you have a group of 4 people, Ann, Ward, Jen, and Al. How many different teams of 2 could you have? Okay, well, let's just think about it. So, Ann, Ward, Jen, and Al. So, we could have Ann and Ward, that's 1. We could have Ann and Jen, that's 2. We could have Ann and Al, that's 3. Okay, we've got all the teams with Ann on it. Now how about Ward? We've already got Ward and Ann. How about Ward and Jen?
24.
Alright, how about Ward and Al? That's 5. We've got all the teams with Ann and Ward. Now how about the teams with Jen? We've already got Jen and Ann, we've already got Jen and Ward, so we need Jen and Al, that's 6. And then we have all the teams with Al on it already, so answer is 6. Okay, so intuitively we know if we have 4 people, we could have 6 combinations of 2. There's also a formula, which we have, which we can calculate that exact same answer. And the beauty of the formula, of course, if we're looking at more than 4 people, we're looking at huge numbers, we can just use the formula. In order to teach you the formula, I need you to be familiar with one concept. It is factorial. So if I have 5 factorial, what does that mean? Yes, this means 5 times 4 times 3 times 2 times 1, which would equal, I don't know, 120 or 125, something like that. Okay, and then 3 factorial would equal 3 times 2 times 1, which would equal 6. Important to remember, 0 factorial equals 1. Does not equal 0. And the way to think about that is, suppose I were to ask you how many teams, let's say I have 4 people, and we already know how many teams of 2 are possible. You can sit there if you need. I killed the power on. I took the power, so you can't use the computer. Or you can sit up here, whatever's more comfortable for you. Okay. Is there no chair?
We need a chair.
Need a chair? You can take this one, or that, or Bashida has a chair. Yes. Okay, so 0 factorial, the answer is 1. If I were to ask you how many teams of 0 out of you 4 could there be, the answer is 1. I would say to whoever asks me that, right, the answer is 0 people are on this team. I would give them a piece of paper and say that's the one answer to that. So 0 factorial equals 1, does not equal 0. Okay, so I promised you a formula to count combinations. That is on the bottom of page 2. It is this NCX equals n factorial divided by n minus x factorial divided by x factorial. N is the total number of objects. 2 is how many x is how many objects we're taking at any one time. Okay, so in answer to the question we just intuitively worked out, all right, we have 4 people, teams of 2. So let's use the formula. 4 factorial. So we have n, this is n, and this is x. The 4 is n, the 2 is x. We have 4 factorial over 4 minus 2 factorial divided by 2 factorial. All right, 4 factorial is going to be 4 times 3 times 2 times 1, which is 24.
Yeah, 24.
Fantastic. 4 minus 2 is 2, so we've got 2 factorial times 2 factorial. So these are just each 2 minus 1, or excuse me, 2 times 1, which is 2. So we've got 24 over 2 times 2, which equals 24 over 4 equals 6. Thank God. Worked out. It would be so embarrassing to do. The answer is 12? Oh my God. All right. Does that make sense? Make sense? Any questions on that? Right. Okay. So let's do a quick example on page 3. Samir is selecting stocks for his portfolio. He has 13 candidate stocks from which he intends to select 8. How many different portfolios of 8 stocks are possible? So Samir is looking at these 13 candidate stocks. They all fit his criteria. They're large growth, information available. He likes them, but he needs to just select 8. And we want to know how many different combinations of 8 are possible. Does everyone know how to solve this problem? Question?
Would it be the same, we're using the same formula? right?
Absolutely,
Would it be
absolutely. Yes, what?
the
Go
same
ahead.
thing, 13i over
Yes.
13 minus 8?
Yeah, 13 would be here,
Yeah.
8 would be here, and you do the formula here. Let me go ahead and write it out, because the challenge in this tends to be the first time people use their calculator. So let's just make sure we understand the math. So we've got combinations, 13, 8 is going to be 13 factorial over 13 minus 8 factorial divided by 8 factorial. Okay. So, does everyone have a calculator? Most people have a calculator. Why don't we take 3 minutes to see if you can get some familiarity with that and give me an answer? Oh, sorry. Yes, yes.
You wrote it out.
No, it's not 40. It's not 40 factorial. It's about, yes. So first you do 5 factorial, so 5 factorial. Then you do 8 factorial, you multiply. All right, if you have the answer, just blurt it out really loud. 1287. I like it. Did anyone else get 1287? Yep. All right, so the motion has been moved and seconded. This is also just a chance to play around with your calculator, so you may not have quite gotten there, but this is just something you'll want to go home and practice and make sure you're capable of doing with whatever calculator that you're using. So we ready to move on to the next subject? Got combinations? Okay. All right. The next thing I want to teach you in our quest to build the normal distribution is the multiplication rule of probability. And we're going to start with the fundamental rule of probability, which is at the bottom of page 3. All right, so the probability of event A happening equals F over T, F being the number of favorable outcomes, T being the total number of possible outcomes in an experiment. So suppose I have a 6-sided die. There are 6 total outcomes. Suppose I were to ask you, what's the probability of me rolling an even number? 3 out of 6 is correct. You would count the number of favorable outcomes. An even number would be 2, 4, 6. So F in this case would be 3, total would be 6. So 3 out of 6 or 1/2. There would be a 50% probability of rolling an even number. What's the probability of rolling a 5? 1 out of 6. There's one favorable outcome, you can only roll a 5, otherwise you didn't roll a 5. And there are 6 possible total outcomes, the denominator is t, 1 out of 6. Alright, basic rule of probability. Next question. Suppose I'm going to roll this die twice. Alright, someone's shaking their head. Alright, what is the probability of me rolling a 6 twice in a row? 2 out of 12? 2, 6? Yeah, I'm not liking the answers so far. Alright, it is not 2 out of 12.
Oh, 1 out of 5.
No, those are for the deli beans.
1 out of 30, you're on the right track. Oh, yeah, alright.
1 6, it's still 1 6.
Alright, you're on the right track. I like what you're doing. You're actually doing an advanced move, conditional probability. But in this case,
Thanks, Andrew.
but it happens to be wrong, but you're because you're ahead of us. The answer is 1 out of 36. So it's 1/6 times 1/6. So the first time you roll the die, 1 out of 6 chance. Second time you roll the die, also 1 out of 6 chance. And how we solve this problem is we think of the total number of things that could happen. I'm going to roll the die once, then I'm going to roll it twice. How many different outcomes are possible? 36, right? There's 36 total things that could be, those ways those die could come up. I could get a 5 the first time, a 6 the second time, I could get a 1 the first time, I could get a 3 the second time, the list goes on. And it's a total of 36 possibilities. You with me?
Why not 2 over 30?
Okay, good, excellent question, yes, okay, so the
I
first.
know the formula, I'm just saying like, why not 2?
Yes, yeah, you're asking the exact right question. So if we're comfortable with the fact that there are 36 total things that could happen in this experiment, how many ways could I be successful at rolling a 6 twice? Are there 2 ways that this could happen, or is there only 1? There's only 1. Alright, so the answer is 1 out of 36. 9. So events favorable, 1. I have to roll a 6 twice. I can't roll a 5 the first time and a 7 the second time. It doesn't work. I have to roll a 6 the first time. I have to roll a 6 the second time. There's only 1 way that can happen. And there's a total of 36 things that could happen. So the probability of this event happening is 1 out of 36. I want to take a shortcut to get there. I know the probability of event A happening is 1/6 the first time, and I just multiply that by the probability of it happening the second time. Multiplication rule of probability, the answer is 1 out of 36. Do you like that? Okay, that is detailed for us, I believe, on the next slide. This is called the multiplication rule, joint probabilities, the multiplication rule. That little box in the center, the probability of A and B happening, that funny symbol, that upside down U, it's called intersection. So the probability of A and B. So this means A and B happening, both happening. Rolling a 6 the first time and rolling a 6 the second time equals the probability of A times the probability of B. Good. Good. Alright, so that's most of the heavy lifting to get us into the binomial distribution. So we're just going to look at those 2 things, combinations and probability, a slightly different way. So don't get scared in thinking I'm throwing more stuff at you. All I'm going to ask you to do for the next 10, 15 minutes is just ruminate on what we know. So let's look at the top of page 5. Let's answer those questions. Suppose you have a 6-sided die. What is the probability of rolling a 6? 1/6. Fantastic. What is the probability of rolling a 6 twice in a row?
136.
Fantastic. 1/6 times 1/6 equals 1 out of 36. Yes. What is the probability of rolling a 6 3 times in a row?
1 out of 220.
Is it 6 times 6 times 6?
6 times 6, 1 6 times 1 6 times 1 6. Yeah,
It's
like
216.
I know you approached it the wrong way, you're just a little, so it's 1/6 times 1/6 times 1/6 equals 1 out of
216.
216. Yes. Yeah, I think you're approaching it the wrong way, just multiplied a few extra something. So this is the answer to 3 times in a row. How about 4 times? No, we don't have 4 times in a row. All right, 4 times in a row, we just add another 1 6. It would be, that might be the 2000 number. Okay, what is the probability of rolling a 6 and then not rolling a 6?
1 out of 6 and then 5 out of 6.
5 out of 36? 5 out of 36 is the correct answer. How are you getting that?
Because the 1/6 is for the rolling of the 6, and there are 5 different opportunities not to roll a 6.
All right, this is event 1, 1/6 probability of that happening. This is event 2, 5/6 probability of that happening. So the answer is 5 out of 36. Make sense? All right. What is the probability of rolling a 6 and then not rolling a 6 3 times? So we got 4 rolls. I want to roll a 6 the first time, and I don't want to roll a 6 the second, third, or fourth time.
Are you doing 5 over 6 times 5 over 6 times 5 over 6?
Times 1 over 6.
Times 1 over 6, right?
Yes,
Oh.
yes,
Is that what we
yes,
call it? What was
yes. So, all right, so we got 4 rolls. The probability of rolling a 6 the first time is 1/6. Probability of not rolling a 6 the second time, 5/6. The third time not rolling a 6 is 5/6. Fourth time not rolling a 6 is 5/6.
125
And that
over
equals-
12.
How much? 125?
125 over 1296.
1296. What's the decimal breakdown to?
Oh. .0964.
Thank you. Okay, 0.0964, or we could also say 9.64%. So there's approximately a 1 in 10 chance of that happening. So if I do it 100 times, then 10 of those times, I'm gonna roll a 6 the first time and not roll a 6 the second, third, and fourth.
And when we're doing like our quiz, you want it all the way down to the decimal of the event, right?
Oh, how much you round to? Yeah, so for percentages, I would round to 4 digits, because as you can see, the important part here is 9.64%. So you're gonna wanna go to 4 digits for percentages.
So
Other numbers, I would go to 2 digits.
So we'll move the 4 up to a 5 then, because
Yeah.
the fifth number's a 5.
Right.
Thank you. Thank you. Fantastic. All right. So what question are we on now? What is the probability of rolling a 6 exactly 1 time out of 4 rolls? All right, so we already know the probability of rolling a 6 the first time and then not rolling a 6 the second, third, and fourth time. Question now is, what is the probability of rolling a 6 exactly 1 time out of 4 rolls? All right, similar. We're
Isn't
going to
it-
use this as our basis for answering this question, but it's not exactly the same. Yes.
Would it be 1 out of 1296 or no?
No, that's less.
Yes.
So that's less. So let me give you a hint. The probability is going to be greater than this 9%. The reason it's going to be greater is because we could now roll a 6 this time, this time, this time, or this time. Any of those 4 times meets our criteria. So the probability of just this happening, 0.65%. But now we have additional ways that we could be quote-unquote successful in this event of rolling 1/6 out of 4 rolls. So it's gonna be higher. Question is, how much higher?
Well, is that what you're gonna do?
Well, to answer this question, let me ask you, how many different ways could it happen? This is one of the ways it could happen. How many additional ways could it happen? How many? 3 more ways.
3 more ways.
Yes, total of 4 ways. Could happen this time, this time, this time, this time. Alright, so what's the if it happens the second time, how do we calculate the probability of that happening?
So 1/6 times 1/6.
But the second time it would be 5/6 for the first roll, times 1/6, because we're gonna hit it on the second time, and we're not gonna hit it the third time, and we're not gonna hit it the 4th time, and what's the answer?
Exactly.
Yes, 9.65%, okay? And there's 4 different ways that this could happen. Each time it happens, this is the probability of it happening. Question?
Oh,
I don't follow.
Yeah, I'm not following
this.
Like 5, 6 times 1, so like you break it down exactly what you did.
Okay, so this is an answer to the question, if we roll the die, and we're gonna hit the 6 the first time, we're not gonna hit it the 2nd, 3rd, and 4th time. So my question to you is, what is the probability of rolling 1/6 out of a total of 4 rolls? So you need to think about the other ways that it could happen. It could happen this way, or we could roll the 6 here, that's the second way it could happen, or we could roll the 6 here, that's the third way it could happen, or we could roll the 6 here, that's the 4th way it could happen. So let's calculate the probability of it happening here. We're rolling a 6 the second time. Okay, so what that means is the first time we don't want to roll a 6. The probability of not rolling a 6, 5/6. Second time, we do want to roll a 6. Probability of rolling 6, 1/6. We've hit our 6, we just hope we don't hit it the 2nd, the 3rd, and 4th time. Probability of not rolling a 6 this time, 5/6. Probability of not rolling a 6 this time, 5/6. And you'll notice that it's the same thing, just in a different order. So there's 4 ways this could happen. The probability of each of those 4 happening, 9.65%. So
so
And do you add
Yes,
9.65?
we add them together, yes.
that's what I was
Yes,
gonna
yes.
say, okay.
So in answer to the question, was the probability of rolling 6 exactly 1 time out of 4 rolls? It's this times 4. 4, which equals, was it 38 something? Thank you. 38.6%. Well, we got it. Okay, so I'm going to stay with that exact same question, to which the answer is 38.6%. But I'm going to ask you to use the combination formula we learned 20 minutes ago to solve this question. Where the combination formula comes in is, how many different ways could this event happen? The answer to that is 4. You could answer 4 ways. A more complicated way of me asking that question is, how many combinations of 1 are there out of 4 rolls? Well, if I have 4 rolls, if I have 4 people, how many teams of 1 are there? There's 4 teams of 1. So we know the answer to that. Alright, so we're still asking questions we know the answer to, but let's just ask a different question. Now let's use the combination formula to solve that question. Okay, so let's do combination, 4 things, 4 rolls. How many combinations of 1 are there? Let's use our formula. Okay, we've got the formula. That's going to be 4 factorial over 4 minus 1 factorial over 1 factorial. Okay, 4 factorial is 4 times 3 times 2, which is 24. All right, over 4 minus 1 is 3. 3 factorial is 3 times 2, which is 6. 6, okay. 24 divided by 6. 4.
And how did you pose the question again, I'm sorry?
How many combinations of 1 out of 4 are there? Out of 4 things, how many combinations of 1? Or we could just go back to our original question. What's the probability of rolling a 6 exactly 1 time out of 4 rolls?
Me? Yeah, I'm with you. I get screwed up listening to the way the verbiage is, so just give it to me in plain English and let me figure it out.
Okay.
So the last one, would that be 6C1?
No, the last one.
When you just mentioned.
This is the only one we've talked about so far. We've got 4 rolls. How many different combinations of 1 are there? How many different ways? Yeah, so 4 things, how many combinations of 1?
And then I got, you said, going back to the first question, how can we do that the same way? So I was trying to figure out.
Oh, okay, let's do that. You wanna do that?
So would it be, 6C1?
It would be 4C2, and the answer would be 6.
1 to 2.
So how many combinations of 2? Is this what you're asking? So the question you're asking me now is, how many different ways could I roll a 6 twice out of 4 rolls? Are you asking me that?
Well, whichever the first question, you said we're going back to the first question.
Well, let's just state this question. Okay. The question we initially asked was, what's the probability of rolling a 6 exactly 1 time out of 4 rolls? Okay. So in order to answer that, we need to know how many different ways could that happen. Well, there's 4 different ways it could happen. Now we could figure that out just in our head because it's an easy problem. We could also figure that out using the combinations formula, which we did. We came up with 4 ways that it could happen. What's the probability of it happening each time? Some variation of this. They all come out to the same thing, 9.65.
So do you use the combination formula when order does matter?
Order does not matter.
When order does not matter.
Order does not matter, yeah.
Okay.
That's right. Order does not matter. Because we don't care whether it's the first, second, third, or fourth one.
Gotcha.
Yeah, and that permutation thing you learned in Turbo, never think about that again.
Oh, no. I'm just asking.
Wow.
I'm being sarcastic. Everything we teach you is valuable, but not for this.
I gotcha.
Okay, so are we good with that question? What's the probability of rolling a 6 exactly 1 time out of 4 rolls? All right, how about the last question there? What's the probability of rolling a 6 twice out of 4 rolls? So, same analysis. How many different ways could this happen? That's the combination part. Second question, what's the probability of it happening each time? So, let's figure out the ways that this could happen for C2. Okay, I've got 4 different rolls. How many different combinations of 2? Order does not matter, because it could be the first and second one, it could be the third and fourth one, just as long as I get 2. And we know the answer to this is what? 6. We can just figure that out by counting. We could also use the combinations formula. Perfectly legitimate way to do it. We know there are 6 ways this could happen. 2 rolls out of 4. 6 different ways it could happen. What's the probability of it happening each time?
2 out of 6?
Well, we're going to use a similar method that we used right here. So let's think about it happening any one time. All right, let's suppose we roll a 6 the first time. 1 out of 6 chance of that happening. And suppose we also roll a 6 the second time. 1 out of 6 chance of that happening. Now we don't roll a 6 the third time. We don't roll a 6 the fourth time.
So it's 25.
And it doesn't matter which order these are in. The math would be the same. It would all be 1 6 times 1 6 times 5 6 times 5 6. Regardless of order. And does anyone have this for me?
25 over 1296.
25 over 1296, what's the decimal?
0.0193.
Okay, or 1.93%. All right, and what do we need to do to that 1.39% to get to our answer? Multiply it by 6, right? Times 6 equals what, 12, 11 something percent? 11.58,
11.58.
thank you so much. 58%. Okay. We like this?
Why aren't you following the same rule for the combination? Where'd you get the 6 from?
Right,
The 6, we did it in our head, but we could have followed the combination formula. You wanna do it? Let's do it. So let's do 4 factorial over 4 minus 2 factorial, 2 factorial? You with me? Yeah, okay. Alright, so 4 times 3 times 2 times 1 is 24. Okay, 2 factorial times 2 factorial is 2 times 2, which is 4, equals 6.
So which, like the homework, which way do we do it? 11.58% or 6?
With the 2-part question is what's
Yeah, it's
happening, right?
it would be a 2-part question. It would be it'd be a percentage, or I could ask you that. I could ask you how many combinations, and you would just figure that out. And hopefully there's a shortcut on your calculator, like if you could actually punch in combinations. But in any case, we'll figure that out on your calculator. Okay, we're good with this? All right, so this is the binomial probability function on the bottom of page 5. Okay. Probability of x. We were using different examples. Probability of 1 time rolling a 6. That would be where we'd put the x in that bottom slot. Probability of 2 times rolling a 6. We'd put a 2 in that number. Probability of 3. Put a 3 in that number. Or 4 out of 4 times. Put a 4 in that number. Take a look at the first part of that binomial probability function, bottom of page 5. See that n factorial over n minus x factorial times x factorial? Does that look familiar? That is our combinations formula. So that is how many ways could this happen? And then the p raised to the x times 1 minus p raised to the n minus x. That is this action here. Okay, so this would be p, our probability would be 1/6, would be raised to the 1, and times n minus 1, so, or 1 minus p, which would be 5/6, and we would raise that to the remaining 3 trials. So this we could look at as 1/6 raised to the 1 times 5/6 raised to the 3. Same thing. We like it? Make sense? Sort of? We'll get a chance to practice, don't we? Okay, let's, right, I'm gonna do this, I see some anxious faces, so let's try this binomial formula. Let's do it for our, let's do it for the second example. Okay, so for this one, we'll leave this up over here. We're gonna leave all this up over here, and we're gonna do the formula on page 5. We're gonna use that binomial formula. All right. So my question to you all is, if I roll a die 4 times, what's the probability of rolling exactly a 6 exactly twice? We're going to solve that question over the next 5 minutes. We've already solved it, we already know the answer, we're just going to use the formula this time. So, take a look at that formula and let's plug in the numbers. So it's probability of 2. Rolling a 6 twice out of the 4 trials. Alright, equals n factorial is the top. There's a total of 4. 4 factorial over n minus x. So n is total number, 4 rolls, 2 is our x, minus 2 factorial times 2 factorial. Alright, we're not done yet. We need this p to the x. Alright, this p is probability of success. Perhaps I didn't clarify that. And the probability of success in this case is 1/6. So, times 1/6 raised to the what? Second power. That is correct. I raise this to the second power times 1 minus p. So 1 minus 1/6 equals 5/6. Five sixths raised to the n minus x. N is 4, x is 2, so I raise that to the second power. And if I do all those calculations, this first part is going to give me 6, and then this second part is going to give me 1.93. And then I want to multiply those together, and I'm going to get 11.58%. You like this?
Yeah. Confused on the last
Confused about the last part.
Yeah,
Which part?
can you go back to that piece right there?
Yes.
So I have p to the x is times 1/6 to the second power, right?
Yep.
Got that. And then the 1 minus p is 1 minus 1/6.
Yep.
N minus x,
N is the total number of trials, so I'm going to roll 4 times. X is the number of successes I'm calculating.
so 4 minus 2. Got it.
And this is, like I said, this is the same question that we just solved. All I'm doing now is putting it into this binomial formula on page 5.
So that 5/6 to the second power is 25 over 36?
Yeah.
Yeah, okay.
Okay, all right, let's turn the page. Take a look at that second slide, the logic of the binomial formula. The first part of this expression, often labeled the binomial coefficient, simply counts the number of ways in which exactly x successes in n trials can occur. It's our combination. Second part of the expression computes the probability of each of the ways in which x successes can occur. Right? All right. Binomial combinations, conditions, excuse me. This experiment involves a number of trials. In our case, it was 4. Only 2 outcomes. In our case, that was roll a 6 or don't roll a 6. Trials are independent. The second time doesn't affect the third time, etc. And the probability of success is consistent throughout. In our case, it was 1/6 the whole time. You like it? All right. Let's take a look at, okay. All right, let's take a look at the example on the top of page 7. The Wall Street Journal reports that 42% of approximately 3,500 stocks traded yesterday on the New York Stock Exchange advanced. That means increased in price. And 58% declined or unchanged. If you had randomly chosen 4 stocks at the start of the day, how likely is it that all 4 stocks you selected increased in value? How likely is it that exactly 2 of the 4 stocks you selected increased in value? How likely is it that no more than 1 of the 4 stocks you selected increased in value? So, how are we going to solve this problem? Let's look at the second part, because I think that's similar to a calculation we've done. Exactly, how likely is it that exactly 2 of the 4 stocks we selected increased in value. So we know that there's a 42% chance that any stock we select increased in value. How likely is it that 2 out of those 4 we selected increased? Well, we're going to use the binomial formula for that. We're going to say, well, how many different ways could we have that outcome? Well, the first and second stock we selected could be the ones that increased. The first and fourth could be the ones, the third and fourth. We're going to use a combination question. How many combinations of 2 are possible out of 4? We know the answer to that is 6. Or we could also just use the formula. And then we're going to multiply the probability of success, 42%, time raised to the second power, because we want that to happen twice. And then we want to multiply that by the probability of not increasing, 58%. And we're going to raise that to the second power, because in this scenario we want that to happen twice. Does that make sense?
Yeah.
Yeah, just if you could, just write that down, just work that, I'll do it in a minute after I erase some stuff on the board. But to just actually write this problem using the binomial formula on the previous 2 pages back. Like actually just write out what you would put in that formula on page 5. Okay, our P, probability of success, 42%. N is 4, because we're picking 4 stocks. Number of times we want to be quote-unquote successful here is 2. Okay, so probability of exactly 2 successes equals. All right, what goes here?
4.
4. Anything else?
Oh.
Factorial, yes. Over 4 minus 2 factorial. 2 factorial times
42 to the second power.
0.42 exactly, raised to the second power times 1 minus p, 1 minus p.
58.
Yep, 0.58 raised to the second power. And that's it.
Oh, it is.
And if we crunch that out, we will get something very close to 35, 36%.
So I'm having a hard time figuring out the variables. Like the math is, like, I get the math, but just understanding the different variables, which the components. Like, can you walk me through the process?
Yes. So, we've got, we're reading that 42% of stocks advance. So that's the chance of success. We don't need to worry about that 3,500. That's just giving us the way they got the 42%. And the question asks is if you've randomly chosen 4 stocks. So we're going to randomly choose 4 things. So we have 4 trials, if you will. It's like we're rolling the die 4 times. Except it's just a die that's like gives us a 42% chance of hitting. So there are 4 total events happening. So N is 4. And then the second part of the question, which we started with, exactly 2 of the 4 stocks you selected increased. It's the number of successes you want in this experiment. So X is 2. Okay, this makes sense? All right. So take a look at the graph on the bottom of page 7. You see we've got a discrete probability distribution. This is in answer to the question above. On the vertical axis, we've got probability on the left-hand side.
to solve this?
Oh, yeah, you can if you want. What'd you get? What'd you get?
Yeah, I'm not finished, that's why.
Yeah, don't worry about it, don't worry about it. You get like 36% or so. Yeah. And the answer is gonna be at the bottom, is that graph at the bottom of page 7. So, if we were to graph all these possibilities, we would have this probability distribution. On the left-hand side, we have probability. On the horizontal axis, we have number of successes. So you can see number of successes. We could pick 0 stocks that increase. We could also pick 1 stock that increases, 2 stocks, 3 stocks, or 4 stocks. And it's giving us the probability of an increase each time. Does that make sense? So this is an important step here. I'm introducing a probability distribution, and I want to make sure you're comfortable with it. So on the left-hand side, we've got probability, the chance of this thing happening, and on the horizontal axis, we have number of successes, 0, 1, 2, 3, or 4. So we've got kind of a curve there. Most likely thing that would happen is we would choose 2. Choosing 1 stock that advances, that's also fairly likely. And then 0, 3, or 4, we're getting into less likely scenarios. Okay, so everyone comfortable? This is a probability distribution. We'll be seeing a lot more of these in class. And we at least have a sense of how to approach the binomial distribution. All right, let's continue with that binomial, and let's do this quick experiment where we're using the binomial probability distribution, and we're going to use this to answer this question at the top of page 8. Suppose we have an experiment where we flip a coin 20 times, and we count the number of times the coin comes up heads. All right, so what's your name? Gabriel. All right, so Gabriel, we have an experiment, n equals 20. 20 different things that are going to happen. We're going to flip this coin 20 times. The probability of it coming up heads each time, 50%. I'm going to ask you all to calculate the probability of the coin coming up heads 0 times, all the way up to 20 times. So let's pick one in the middle just to think about. What's the probability of you flipping heads 8 times out of those 20 possible flips?
Isn't it half times 8?
What's that?
Would it be 1/2 times 8?
No, it would not, because you're gonna have 20 total flips, because you need to consider the different combinations of ways that could happen. The question you're giving me the answer to is, what's the probability of flipping a coin and having it come up heads 8 times in a row? The answer to that is what you said, 1/2 times, 1/2 to the 8th power. So, all right, we've got 20, we're gonna flip this coin 20 times. And each time there's a 50% chance it comes up heads. What's the probability of me getting exactly 8 heads? How do I solve this problem?
Binomial.
Yes. First thing I need to know is how many different ways this could happen. I could get heads the first 8 times in a row, and then the next 12 times I get tails. Right, you get heads the first time, the third time, the fourth time, this 12th, 13th, 14th, as long as it adds up to 8. How many different combinations of 8 of 20 things total are there? So, P is 0.5, N is 20, X is 8 in this iteration. of 8 equals 20 factorial over 20 minus 8 factorial times 8 factorial times 0.5 raised to the 8th times 0.5 raised to the 12th. You like that?
Wait.
The other calculator,
Oh, I
did
get it, I
20
get it.
factorial in my phone calculator.
20, you can't do 20 factorial? Wait, do you have a cell phone? Yeah. So you do 20 and then x factorial. And it's 2.4 times e to the 8th, it's e to the 18. So it's like multiply that by 18 zeros. I think that might be it.
So that's 2.4?
No, it's 2.4 times e to the 8th. I don't know what that means. Divide it by a million and see what happens. And they keep dividing it by a million and then you'll get it'll hit on a manageable number. Yeah, you're just gonna have to get used to that. That's what you're doing. Can you keep that in your calculator and divide it by whatever you get down here? And then maybe you'll get a manageable number?
That's just my way of, does that make sense for you? I wrote that on the side here.
Alright, does someone have a way of solving this with their calculator?
I don't know how to do this. What's the factorial function on the calculator? Does it show up as the exclamation point?
Yeah.
Yes, usually does.
It does?
Maybe that's gonna be under like a math function. Yeah, that'll probably be under a math function. Is there math?
Well, that's a huge
So if I divide by a million, it's a big number,
But it's an actual number.
Yes.
Okay, yeah, alright, so now we're
Number
done.
2.
So, yeah, so it's
Can't figure out
this
the factorial.
plus 6 zeros. That's the answer.
Oh,
And it was Andrew.
okay.
Andrew. So maybe if you keep that big number in your calculator and divide it by whatever you get for this, then it'll come out to a manageable number on your calculator. Okay. So let's just solve this. I do sometimes like to do this thing where I try to give individual people a chance to solve 0 through 20. If we just solve this, I would be happy. Does anyone have an answer? You got 12%? Okay, close. Close.
What I gotta hear is scientific. I don't know how to put this to the top power.
Alright, so 20 factorial.
He keeps giving me that plus 8, E plus 18 crap.
Yeah, that's just how many zeros you need to add
10
to it.
zeros after?
Yeah. Yeah. So divide that by, see if you can you divide that by, use parentheses and divide it by 12 factorial times 8 factorial? Or maybe, better yet, maybe you can, no, you're gonna get some large number. Okay, alright, so this is the kind of thing I would like you to go home and practice using your calculator to solve. You could also use Excel. There would definitely be a way you could do it there. I can work with you in your calculator a little bit after class, but we're probably gonna be tired and frustrated and wanna go home. But I will stay if you wanna do a little calculator work after class. But you're just gonna need to figure out how to work your calculator to solve this kind of problem. And if you're getting that big E, big whatever,
Well, the
you
factorial, I got.
need to figure out a way to keep that in your calculator and get it into
Supposed to be in
a
a trillion?
This will be in the trillions.
That's,
But
that's
the
204 trillion.
The ultimate answer will not, because you're gonna be dividing it by a really big number. This would be like a trillion. What did you get?
125,970.
125,970. Okay. So then can you multiply it this times this?
Yeah. Just figure that out.
This one's better?
Yeah, I can do the function.
I found a calculator online and it came out
I got the numbers for those.
to .12. You said that right?
0.5 to the 8th power is 0.0039.
You said it's a little thing up like.
Yeah, it's an up arrow.
The answer, is the answer .12 no?
Well,
I did it like 0.17 something. Yes.
to get that, can't you just do 20 factorial divided by 12 factorial, right?
Times 8 factorial. Can you do the time? Yeah. 20 factorial divided by 12 factorial.
And then that.
Times 1 over.
And that, no, what I did was I got that same.
Divided by?
Then
Divided
I
by?
divided it by the 8 factorial again.
Yes. Yeah, try this in your calculators. Try 20 factorial divided by 12 factorial divided by 8 factorial.
I got 125, yes.
Yeah.
When you put in parentheses, the bottom, it'll go.
Parentheses is another way to do it, or the way you can do it, your neighbor does it, one at a time would work too.
Yeah.
Try it, so you're
I'm
working on
working
this?
out the, yeah.
Yes.
Do you want to do 20 factorial divided by 12 factorial divided by 8 factorial?
Yes, you got it.
25,970.
Okay.
And then,
And then multiply it by 0.5 raised to the 8 times 0.5 raised to the 12.
that astronomical
This is
number.
12, I wrote this, I wrote
Divided by
8.
12
It's supposed to be 12.
It gives me 0.120.
And then divided by 8.
You want the whole thing?
1, 2, 0, 1, 3, okay.
Is it
Okay.
0.098,
That's, yeah, that's the answer.
0.0983? Is
That
not
is
it?
totally right. You are so right.
You were right along.
I'm so sorry. Right on.
So right, so wrong.
So right so long ago. The answer's 12%. Good job.
But that was on the chart.
Like 12%. Yeah, the
Why is
answer's
it
on the chart.
12%?
I was looking at the wrong thing on the chart. My bad.
Wait a second.
Why is that 12%?
That point nine.
I just multiplied this times 0.5 raised to the 8 times 0.5 raised to the 12.
Okay, that's what I did.
Get from 5 to the 12.
What'd you get, 7 trillion again?
Because 0.5 raised to the 8th is 0.0039.
Okay, I believe you.
And then 0.5 raised to the 12th is 0.0002.
Okay, so multiply those
So when you
together.
multiply that by 125,970, you get 0.0983.
The answer is 12%.
0.09, so it sounds like it's close.
You gotta multiply it all across. though.
Yeah, we did.
Yeah.
Oh, you gotta multiply all of those numbers?
Yeah.
So this times
So
this
then-
times this.
Okay, because I was just doing the 4, rounding it to the 4, so.
Okay.
Okay,
Oh,
now I see
so
it.
it's a rounding? Okay, maybe a
Yeah.
rounding
You
error.
said to round to the 4, right?
I'm just
Round
listening.
to the 4th for your final answer, but when you're working with numbers this big, you want to keep them in your
All of
calculator.
them. Okay. That's what it is.
Yeah, the problem.
All right, I'm a little behind schedule, but I'd like to keep going for like 10 minutes and then we'll take a break. Is that okay with you? Okay, so bear with me here. Let's take a look at the bottom of page 8. That is the binomial distribution for this experiment. So if you were to flip a coin 20 times, the chances of 8 heads, as your colleague pointed out 10 minutes ago, would be 12%. Like you can look at the bottom of that chart and and see the number 8, probability of success, or number 8 successes, the probability is 12%. Any of those, what's the probability of flipping 10 heads out of those 20 times? 17, yes. What's the probability of 14 heads?
3.
Yes. What's the probability of 20 heads? Extremely small. Okay, so tell me about that shape, the distribution of that probability curve.
It looks even.
Looks even? All right, does it look familiar?
Yes.
Where have you seen it before?
Binomial distribution.
Standard normal, maybe?
Multiplication.
Standard normal? Normal distribution?
Combination.
So this could be called a classic bell curve.
Yeah.
We're gonna call it a normal distribution.
He said that.
Yes. So normal distribution, so again, I threw a lot at you quickly, and so sometimes you had some calculator issues and just working out the kinks with this, but we got there. Like, we were able to solve at least one of these, and if we spend more time on it, we could have solved all 20 of them. So this distribution, you could have calculated. You could have calculated each one. And if you had graphed it, you would have graphed the normal distribution. The most important discovery in statistics is something that you just partially recreated. You have the skills to calculate the normal distribution. Now, next question. If I were to send all 18 or 19 of you home and said, do this experiment tonight, flip a coin 20 times, write down how many times you get heads, and then we come back next week and we graph it, we put it on a graph, what would the distribution look like? Would it be this perfect bell curve?
No.
Would it be kind of close to this perfect bell curve? Maybe kind of close to this perfect bell curve. But since there's only 19 of you, maybe a couple of you would get really unlucky and only get heads 4 times. And then, it would look something like this. Next question.
Don't we have to consider the variables involved, though, like how hard we toss it and all the other things that are involved?
Great question. Do we?
No.
What about the weight, if everybody's using a coin?
We're assuming everyone's using a fair coin.
Oh,
So
okay.
what is the possibility of flipping heads? 50%, right? Unless you have a magic coin, right? Yeah. If you flip it really hard, does that change your odds? Not really? Yeah.
What exactly, I mean, I understand what you mean by a definition of a fair coin, but if you were actually doing an experiment, would you manufacture something, or would you use a penny or a dime? Because the reason I ask is because I had heard one time, and I forget which way it goes, but something that even though that you think if you're flipping, say, a penny, heads or tails, that it should be a 50-50 proposition, but because of the way it's manufactured, it's a little bit more weighted on one side than the other. So it's just like when you're using a fair coin, what exactly is your definition, or what's your example?
So we're gonna assume this coin is fair, and that there's a 50% chance of getting heads, 50% chance of getting tails. If you have a magic coin, I would love to see it. Also, if you could tell me whether or not I should guess heads or tails next time there's a coin flip, because there's a slight. Okay, so but we're gonna assume this is a fair coin. Is that fair? Fair enough? Even enough? Okay, so for now we'll assume it's a fair coin. 50% chance of heads, 50% chance of tails. I already asked you if you all went home and we graphed this would look kind of like this. Next question I want to ask, what if we sent every single Mercy College student, and there are 10,000 of them, we sent them home, told them to do this experiment, and then recorded the results? What would the distribution look like?
Probably all over the floor. It would look like that.
It would look pretty much exactly like this. why would it look pretty much exactly like this?
Bigger sample.
Larger sample, they would ultimately fall into that probability. If we have large numbers, it's going to match this probability. So that's the second important step in understanding this. If we were to send a large number of people home, then it would mimic this probability. That's kind of amazing, isn't it? We would know what's going to happen with these 10,000 students before we even send them home, because we can calculate the probability. So we would know what this distribution looks like. So the third question I want to ask. Now, in our calculations, we know that the most likely number of heads is 10. And that makes sense, of course. 50% chance, assuming a fair coin. 10 times it's going to be heads, 10 times it's going to be tails. We know that from our calculations. Suppose we didn't know that. Suppose we didn't know what it was, and we wanted to find out what it was. And we wanted to find out by asking those Mercy College students who we sent home. And we can't ask all 10,000 of them. They'd say all 10,000 of them do this experiment, and they write it down. But we can't manage all 10,000. We can't ask all 10,000. Suppose we just ask one of them. What is the probability that Mercy College student is going to tell us the answer is 9, 10, or 11? What is the probability they're going to tell us the answer is 10? 17%, right?
Oh, it's still the same distribution.
Yeah, we just don't know what it is. It is the same, we just don't know what it is. We're trying to find out what it is by asking a Mercy College student. So there's a 17% chance that this student is going to tell us, well, I flipped a coin and I got 10 heads. So what are the chances that any one student is going to tell us they got a 9, 10, or 11?
16 or 17%.
So 9, 10, or 11. Add them all three together. Yeah, 50%. So there's a 50% chance that just by sampling one student, the answer is going to be within one of the true mean. And remember, in this assumption, we don't know what it is. We don't know that the average is 10. We're trying to sample and figure out what it is. We ask one person, there's a 50% chance that we're going to get within one. So that's pretty good chances of getting close to the right number just by asking one person, right? What if we ask 2 people? Or 3, so let's say 2 people. We ask 2 people. Now, there's no quite right or wrong answer to this. Where I'm going with it is, maybe one of those students would have gotten really lucky and flipped their coin 15 times. But the other student probably was in the 8, 9, 10, 11, 12 range and would have evened out that extreme outlier, that person who got lucky. Because the chances of both of the people we ask getting really, really lucky gets to be very, very small. So remember we said the chances of getting 20 out of 20 is like less than 1%. The chances of 2 people getting 20 out of 20 extremely, extremely small. So just by adding that second person, we're able to counterbalance some sort of sampling error. So imagine if we were to ask, say, 30 students. What did you get last night when you did that experiment? Randomly, we select 30 students, we ask them all, we average their number. All right, what do you think we would get for our average in this trial? Well, the answer I'm going for is we would get something probably close to 10, just by asking 30 students. Because we know any one student has a 50% chance of telling us 9, 10, or 11. And we know we might have some outliers, but we have just as much chance of canceling out those outliers. So that's the takeaway from this graph, is that there is a distribution that it will fall into based on probability. And if we don't know what it is, we can get pretty close to it just by random sampling. Okay, so let's take 10 minutes. Let's come back at 8:25 and finish up.
Hi Nelly. How you doing today? See you. Good. Yeah. Well, I'm good, right? Every day.
So, let's take this first one, right?
Yes.
I got you. Sure. How you doing? Nice to meet you. How you doing?
I'll take my call this week too.
Yes. So this is 0, so that goes away. This is raised to the 4th power. And this is 1. Cancels, it goes out at 1.
And this is 0 because.
Yeah, 4 minus 4 is 0. And 4 minus 4 is 0.
Right.
So anything raised to 0, because it's 1, it just cancels out. So all you're left with is 0.42 raised to the 4th.
Right, which is
Which is the same. 0.42 times 0.42 times 0.42.
No, I was signed up for that.
Well, doing it this way. With, I understand that.
I'm taking an online class.
We kind of lost me on this side. And then we were trying to figure out, multiply it by 4.
That to be my.
It's not, it doesn't. Which is, it's just, I look at it, go, you didn't.
Check my thing.
See, I work in Washington, so it would have been smarter for me to take it down.
I think
I feel like this is just something you're just gonna need to.
Yeah, I figured.
There's some homework problems that we'll walk
Lights
through
are lower
this.
than 9 credits.
I can totally stay with you after class, but I think your brain's gonna be so fried by the time we get
No, I
done.
get it.
Yeah.
I mean, this is the same thing that I was while I was doing,
So we can all find a gauge together.
So I'll just, go ahead.
Take a breath.
Yeah.
Okay,
Thanks.
excellent. You bet.
Oh, okay.
You good?
Yeah. I just solved everything. Hey.
That's it.
So here's what I need help with. Bring my calculator next week and to know how to use.
I just figured out how to do that, so that's easy now.
I'm going to.
money, wait a minute.
You have it, if not, I gave her and then I'll give her money.
Yeah, but I need for the vending machine, is that what we're going?
Oh,
Great to have you in class.
well, I just gave,
I'm not the
no,
best.
she said now or later.
So on Black Boy,
I'm gonna practice that.
Yes, Alicia, you better bring your money, cause I ain't got any.
Yes.
I just made the height today, it's so funny, I make you laugh.
Well, I mean, this class you helped me in Turbo, I
Yeah,
flew to that part of Khan Academy after that.
good.
Yeah, combination meditation, I know that formula by heart now.
What we're gonna do now is just similar stuff that we did in Turbo, the Z distribution.
Yeah.
The only problem is it's like the important thing, the more important thing in class, and everybody's gonna be tired.
Yeah.
But I'll try my best.
It'd be good. That'd be good. I still have my notes from this summer too, so.
Okay.
That'll help.
that was Monday.
No, it wasn't, they have a Zoom meeting, it was just like introduction.
I thought it was started today.
Is it turned on?
It says there's no signal or something.
Portion, summary,
No,
turn it
midnight definition.
Oh,
Midnight Friday.
not turned
It's
on.
like the update.
There you go.
June
Boom.
24th. The summary is June 24th.
Oh, my gosh. I swear to God, I pressed that button like
Yeah.
twice.
It's all right.
Right here, you see these?
I believe you.
It's working.
These are the questions I do not see.
That's fine.
That's fine. And he said, he wrote a thing and said, if you don't have to look at it, you can come with me. Because this is small.
Ah, Jonathan.
What's up?
Now it says no. I
I
saw the Microsoft Word thing.
Oh, yeah, I bet the next one just came out. But on.
I tried putting the blue one in and then.
This book was
Alright.
When you register, it has and you get the free shipping. So for books.
Okay, so Blackboard, I can go online and sign up for that.
Yeah, you can get it through university. And use it
Alright.
as your idea.
Just keep going with what I've been doing.
Yes.
Go to, are you on?
No.
Alright, so.
Yes,
Yeah, I just need
yes.
one.
Yeah.
Why was it not in this one? That's not.
Oh, yeah, well, it's one, so what's
It wasn't working, it was wrong.
what's 1 minus 0.5?
I know it was.
Okay. Just want to make sure, thanks.
You got it, you bet.
You can transfer the number?
No, the package you put. You never did on?
The register.
The register, yeah, what you.
Your Mercy Connect?
I mean, the Fez.
No, not fast food, no, we register for classes. How you get it? They didn't give you guidance or anything?
Do the form,
But she didn't give you like.
I did do something, yeah, I did do it.
It's that same thing about. Oh, I thought that's what I said, yeah. I'm gonna wait.
Oh, take your time.
I'm just going through my emails. I haven't looked at them in a couple of days.
I have to email you or see. It's the same thing, Brenda, if you have.
If not, I could do it.
Why is this upside down?
I gotta figure out this.
Is yours upside down?
I know I did it, but I don't remember.
Yeah, I think you could, if you call them, they really is good, like, but look, come to this, I'll show you.
Oh, you cool?
Once you go to that.
Oh, no, you're doing it wrong.
We're doing that.
Actually, can you do me a favor?
If
And I
everything,
can show you some stuff at the same
once you
time.
figure that out.
Can you go open up, Internet Explorer, go to Mercy College Blackboard, log in?
You see all the important things.
Is your office down here or up at Dobbs or?
I have an office in Dobbs, I'm not there very often.
Oh, okay.
Well, you can check out Mercy College Blackboard.
If you go to the Mercy Connection,
It's over space,
and then you see that he has a meeting.
space, Blackboard.
So here it has notes.
Never mind, scratch that.
I know. No, but then I don't want to do,
What's the cheapest you can go
the rental thing. I like residents.
for? Ain't not that bad then. I thought it was $90,
Yeah,
you know.
so that he has his house and stuff. So that's good, whatever.
Just to know about your work,
Okay, so, Grant,
Okay.
so, everything is in the course material.
Orlando.
And then for your Excel, you'll go to Excel exercise data. You'll click
Mike, you know that? I seen him. Yeah. You're right. So early, you didn't know it was that. Alright, so I'm gonna move on there.
Yeah, I'll go tomorrow.
I didn't write it down. I gotta do one of those, send it to me.
It's the same,
Okay.
once you do that, the blackboard, or everything, basically, for that, everything we do everything for blackboard. Everything is supposed to be, yeah, so the same thing, and then everything is supposed to be. Right? Well, you can, it's cheaper to buy, you have that option, too. I just.
Oh, really? How much is that?
They got the.
Buy it on Blackboard?
No, like you go to
Oh, okay.
or Barnes and Noble, or
I'm totally good.
there's textbook.com, check.com. So they all have that option. Yeah, it's not, so, Jada, they have all
It's like night and day.
Oh, who was it?
Every book.
What's up, bro?
Yeah, that's what I'm saying. That's what I'm trying to do. We all gonna be working together.
Richard here? Yes. Jadea Davis?
Jada.
Jasmine De La Cruz?
Joseph De La Cruz, I'm here.
I just say Jerry, I didn't correct that. Shamika? Gabriel? Barbara?
I'm here.
Mary Annie?
I'm here.
Omar? Andrew? Andrew Morales?
Oh.
Yes, sir. Victor? Victor Quinzo? Nelly? Nelly Santiago Rivera?
They here, they're the ladies.
Raymond Smart? Raymond Smart?
Brandon?
Raymond Smart? Carlos? Present. Thank you. Okay. Derek Thompson? Derek Thompson's not here? Okay, so I'm missing Derek, Raymond, Victor.
You guys don't do turbo? When do you guys do it? Oh, February. Okay. We all did it like together. Here, in July. Depends on you know each
Derek's right there.
Hey,
He was taking attendance.
what is me?
Derek's here?
Derek.
Oh, and
Okay.
Victor's here too. Victor's
Derek?
announcing.
Derek?
Yeah.
Oh, yeah, I'm
Derek.
too, my guy.
Victor's here?
Victor's in the, yeah, he's.
Raymond here?
I don't know who
I
Raymond
don't know, I'm
Only Raymond. Okay. Not here.
Yeah.
Not here.
Yeah, me and Victor are here.
Oh.
What's that?
You're very welcome.
Just after class.
Okay, well, he's starting to teach, so I'm gonna be after class.
All right, ladies and gentlemen, I love it when I'm able to get you out of class early.
Yeah.
Unfortunately, that's not gonna happen tonight. But I will get you out of class right at 9:30.
Cool.
For sure, I would never keep you out for 9:30. Unless I'm trying to tell a really funny story.
Okay, wait, no, I think I heard you.
That water bottle with a picture of each other.
On my knees. Alright. So, on the bottom of page 8, we found the normal distribution. You all calculated the most important discovery of history statistics. You did yourself. Congratulations. When we have this normal distribution, we know things about the characteristics of it. We know the probability that it's going to fall into, and we can do things like sampling for a very small number of people, like say 30, and be very confident that we've got a good estimation of the center of that data. As long as we know two things on the top of page 7. One, the expected value. 2, the standard deviation. The expected value is actually what we're sampling for. That's the average. If we played a game like, let's just assume we didn't know it, guess what it is, we would find out that it would be 10 in that experiment. The standard deviation is the spread, the distribution. All right, is this a fat bell curve, or is this a really thin bell curve? Let's look at the bottom of page 9. That example is just picturified right at the bottom. What is the difference between these two frequency distributions? Take a look. We've got one that's really fat and one that's really thin. So what does that mean to you about the distribution of this data? Say we're doing the same thing 20 times. What would the one on the left represent? What would the one on the right represent?
Well, the one on the left would have a wider distribution, and the one on the right would be narrower and more.
Yeah, what does that mean, wider distribution or narrow distribution?
Bigger sample?
Oh, big sample? No, because you can have like a sample of at least 20 and still get those type of curves. So
Yes,
it's-
yeah.
So, give me a second.
Take that.
So it's just that the information that you've got in the first one has a wider spread, where you can have outliers.
Yes.
As opposed to,
Yes.
or you would have more outliers with the first bell curve as opposed to the second one. You would still have outliers, but the majority of your information would be more to the median, to the
More,
center.
yes, more people would get a 9, 10, or 11 on this tighter, thinner curve, right? In the fatter curve, we have more people getting like a 5, 6 heads, or 15, 16, 17, 18, 19, 20 heads. It would be higher probability with this fatter curve.
Are they both still 50% and 9, 10, 11 in both of these curves? Is it still
Not
50%?
necessarily. Yeah, I think if you actually look at the height, you would see that the thinner one is taller in the middle. So we're talking maybe like 70% of your data would be right within 1 or 2. So, alright, so that's just the spread. So if we know the standard deviation, we know the mean, the center of it, we know it falls into a normal distribution, which is what we calculated. We know that it's gonna follow normal laws of probability, then we know a lot. Because you can see these curves are symmetrical. Also, we're able to calculate the percentage chance of being in that top or up tail, the percentage chance of being in the lower tail. We're able to make those kind of assumptions when we can assume a normal distribution. Top of page 10, it's got our normal distribution. Like I said, that we know those two things, the mean, which is that U letter, and the standard deviation, which is the O with a little hat on it, sigma. So the U is sometimes called mu. The standard deviation is sometimes called sigma. We'll just call it standard deviation. If you look at the bottom of page 10, two parameters, the mean, the standard deviation. The highest point in the normal curve is the mean, which is also the median and the mode. We'll talk about that in a minute. The normal curve is symmetric. 50% probability on the left, 50% probability of being on the right. Key characteristic of a normal distribution, it is symmetric. Your probability of flipping a coin and getting 20 heads is the exact same probability of getting 0 heads, because they are polar opposites. Top of page 11, key normal distribution properties. So because we can assume normality, because we can do those calculations like you all did, we can tell how much of the data will be under which parts of the curve. Now let me just fire these 3 pieces of information at you and we'll discuss what they mean. Number one, approximately 68.3% of the data will be within one standard deviation of the mean. So within one standard deviation of the center. Approximately 95.5% of the values will be within two standard deviations. Approximately 99.7 will be within three standard deviations. So what that means is that we have our normal distribution, alright? If we know the mean, alright, and we know the standard deviation, we can say, alright, the mean is here, and one standard deviation, this is 1 sigma, one standard deviation, alright? I gave you a simplified example earlier. I said, what are the chances of being between 9, 10, and 11? That's an approximation. So, one standard deviation, we don't know exactly what that number would be, but we know that there's a 68.3% chance of all the data being within that range. All we need to know is the mean and the standard dip. We also know that within two standard deviations will be 95.5%, and within three standard deviations will be pretty much all the data, 99.7. Because this bell curve follows mathematical principles the same way the binomial curve that you calculated followed. So not only can you calculate things like this, but you can also calculate what line marks the top 5%. Alright, what line marks the top 1%? Alright, if we know these two numbers, we can plug that in and find it. We're going to do some examples of this, and that may shed some more light on it, but I see some sparks, so I feel like you're at least with me so far. All right. So we've got the Z table here. How do I want to do this? So the Z table, tells us essentially percentage of the data that is within a certain number of standard deviations. Let me define Z-score for you before I go any further. So let's look at the bottom of page 12. You see that Z-score? All right, the Z-score is X minus U divided by sigma. So X, which is a certain test statistic. U is the mean, the average, and that sigma sign is the standard deviation. So let's say in our flipping heads and tails example, you go home and you flip a coin and you get 16 heads. All right, that's X. That's your test statistic. The mean, the U, is 10. We know the average, the expected is 10. We did the calculations. And let's just say we were to calculate the standard deviation, which tells us how much the spread is. Let's just say it was 3. Okay, so the Z-score for your experiment of 16 heads is going to be 16 minus the mean, which is 10, minus our standard deviation, which is 3. So 16 minus 10 is 6 divided by 3 equals 2. So what that means is you were 2 standard deviations above the mean. And the reason that's important is because we can define percentages on the standard deviation. We can tell you just how many people, what percentage of people were less than you on that standard normal distribution. So, I'm flipping around here a little bit, but I feel like I haven't quite lost anyone yet. So I'm going to keep going. Let's turn to page 13, and let's look at that example on the top. I've got a standard normal distribution. All right, I've got that curve, and I'm going to assume it's normal. I'm going to assume it's normal because I'm told it's normal, or because I've done some calculations and I can tell that there's nothing skewing the data, it's gonna come out to a normal distribution. And I know that someone who does this experiment by, say, flipping coins has a z-score of 1.2. All right, that person is 1.2 standard deviations above the mean. So that means they flipped heads a few more times than the average person, such that when we calculated their z-score, we got 1.2. So I can look on the standard normal table, also known as the z-table, and I can say, well, what percentage of data is less than a z-score of 1.2? So, on the left-hand side, I look, it says z, the far left. I go down to 1.2. I would go across to the right. It's 1.20 is the number I'm looking for. If I were looking for 1.29, I would go all the way to the right. But I'm just looking for 1.20. So I see 0.8849. What that tells me is that 88.49% of the data is less than a z-score of 1.2. How do we get all these numbers? Well, someone did what you all started to do with those binomial calculations, where we could have calculated all 20 possibilities, counted up the percentages. Someone calculated not just 20, but every single possibility in between 0 on a stand and whatever on a standard curve. And they came up with percentages under the curve. The same way you all calculated, well, there's only a 1% chance of getting up and getting 20 out of 20 heads, or less than a 1% chance. That means you're in the highest 99% chance. This is the same thing. It's just with every calculation in between. So, someone says they have a z-score. They're 1.2 standard deviations above the mean. That person, on a normal distribution, we know that since this distribution is symmetric, 50% is in the upper half, 50% is in the lower half. We know this person with a 1.2 z-score, we know that 11.5% of people are higher than her, and we know that 88.5% have a lower outcome than she did. Does that make sense? Okay. So, what I want to do now is I want to skip right to my go-to example, because I'm excited that you all seem to be with me, and I just want to put this in context with an example right away before I give you anything more complicated. Let's go to the top of page 15. Alright, suppose I have information on the average height of an American male. And I know the average height of an American male is 70 inches. And suppose I have information on the standard deviation, which means how diverse that pool is 3.5 inches. If every American male was very similar in height, then we would have a small standard deviation. If every American male was typically not the same height, then we have a larger standard deviation. So let's just say we have those numbers. We have the mean equal to 70. The standard deviation equal to 3.5. All right, suppose further Michael Jordan has a height of 78 inches. Is that above the average?
Yeah.
All right, how much above the average?
2 standard deviations?
Yeah, something like that. 8 inches above, so 2 plus standard deviations. Tell me exactly how many standard deviations, and to answer that question, let's just find his z-score. So the z-score for MJ is 78 minus 70 over standard deviation 3.5. Hit me.
2.285, so.
All right, 2.3? You like 2.3? Let's say 2.3.
2.3, 2.285.
Okay. Actually, no, I don't want to set a bad example. All right, 2.2.
2.857.
2.29. Okay. Okay. So what is the probability that a randomly selected American male will be shorter than Michael Jordan? How do we solve this question? Yeah. First we use the z-table. Height is something that we could reasonably expect to fall into a normal distribution. One, because there's such a huge population. So,
0.9890.
okay, so the z-score is 0.9890, or not the z-table, the area under the curve for that z-score. All right, so 98.9% of people are going to be shorter than Michael Jordan.
So you say 98.9% of people?
Yep. Yes. Yes.
And that's your Z.
So his z-score was 2.29. The area under the curve associated with the z-score of 2.29 is 98.9%. So where does Michael Jordan fit on this normal distribution? Is he right here? Is he right here? Is he right here? Yeah, right about here. This is MJ. All right, and we know that percentage of people taller than him, what's that, 1.1%? 1.1% of people are taller than him. So if he goes to parties, he has a 1.1% chance of being shorter than someone in the room. Now that's not really an accurate question because it's not a fair sample, it's a biased sample. Because Michael Jordan probably hangs out with basketball players, right? So if he goes to parties, there's a chance that people are going to be on the average taller. So if he had a big list of every single party he could go to in the entire country, and he cranked some lottery wheel, and like pulled out, all right, I'm going to go to this particular party, then that would be more reflective of a, almost 99% chance of him being taller than anyone in the room. Okay. Suppose further Isaiah Thomas, short guy, has a height of 69 inches. What is the z-score for his height? Z-score 69 minus 70 over 3.5 equals negative. Yeah, negative is right.
0.285.
0.285. Okay. All right. So where does Isaiah Thomas fit on this bell curve?
On the beginning.
What's that?
The beginning, right?
No, not quite. This is a tough one. So it was not a completely fair question for me to ask because it's fairly close. What I'll point out to you is it's fairly close to 0. If it were 0, it would be right in the middle. So it is just a little bit to the left of 0. Isaiah Thomas. Okay, now, the thing about the z-table is it is symmetrical. Probability below the median is the exact same probability above the median. This curve breaks exactly the same way, just like it did with the heads and tails experiment. The chances of getting 5 heads is the exact same chance of getting 15 heads. So we can use our z-table. And I skipped over this one, I guess, but there's a larger z-table, so you don't have to use a magnifying glass, on the back of page 11. Right here. So let's look up the z-score for 0.28. Let's call it 0.29. Alright, so on the left-hand side we go to 0.2, and then we go across to 0.29, and we get 0.6141. Okay, so that's the area under the curve for positive 0.29. If his z-score were positive 0.29, which is not, then 61%, it would be like this. Let me get a different color. I can erase. Alright, then 61% would be in here. 61%. Okay. If it were positive. What we can take from that is what's the difference between 61 and 50? 11%. So we can just use the mere opposite of that and say there's 11% difference between Isaiah Thomas and the mean. So we're going to erase this funny color. And we're going to say that 39% of people are shorter than Isaiah Thomas. You like that, John?
Just one more time.
39% of people are shorter, males are shorter than Isaiah Thomas. The next guy who walks by that door, there's a 39% chance he's going to be shorter than Isaiah Thomas. Okay, so last question I think on this slide, don't get excited. Last question on this slide is, what are the chances that an American male, i.e. the next guy who walks by, will have a height in between Isaiah Thomas and Michael Jordan? Well, what's your name again? Richard?
Richard.
Derek. Alright, so 39% of people are shorter than Isaiah Thomas. 1.1% of people are taller than Michael Jordan.
Also, don't add it.
Where does that leave here? So, 39% of people are shorter than Isaiah Thomas. 1.1% of people are taller than Michael Jordan. What percentage of the people are in between?
61.
60? Yeah, 50, 59.
9.7.
I know, I did 11, because you had the difference between the 39 and the 50 was 11, and then you got the 50, so 61. That's what I did.
59.9.
I see where you're going. It is a matter of adding these up, but the thing that you need to add up in this particular question is this and this. You need to subtract both those from 100 and you get the answer.
So you added
59.9.
you added the 39 and the 1.1,
Subtract that. How much?
so that's 40.1, and then subtracted that from 100. Okay.
So just look at it, detail. Like 39% of people are shorter.
Yeah,
1.1% of people are taller. So what does that leave?
everything in between.
Everything in between?
Yeah.
Yeah, whatever it is.
Okay.
All right. How are we doing with this? We like it? Okay, good. Let's try that next example, bottom of 15. Suppose the driving distance to work for residents of a certain community has a mean of 23 miles and a standard deviation of 3.6. What is the probability an individual drives between 19 and 26 miles to get to work? Assume that the distribution is normal. Assuming the distribution is normal is key here. Because once we do, and we have the mean and the standard deviation, we can calculate an answer to a question exactly like this. So for this one, we're gonna need 2 z-scores. We're gonna need a z-score for 19 miles. We're gonna need a z-score for 26 miles. And we're gonna do the same type of thing. Let's add up the space in between type deal. All right, so you process that for a minute. Let me make some space here. All right, so let's get the z-score for 19 first of all. Z-score for 19 is going to be 19 minus what?
23,
Yes, divided by what?
3.6.
3.6, yes, equals
12 plus 8,
12? That sounds a bit high. I think it's,
oh, negative.
It's negative. 6.3. Negative 4.
Negative 1.11.
negative 1.11, I like that.
Yes.
All right, so how about 26? 26 minus 23 over 3.6 equals, nice, 0.8333. Okay, so we've got our normal distribution. Alright, we have a mean of 23. We have a standard deviation of 3.6, and we can assume normality. So we've got a z-score of negative 1.11. Alright, this is the center here. Call that the center. And we've got a z-score of 0.833. So this is z. Z's. Okay, so what do I do next? Actually, let's not look at the chart next. Let's just think about, I did something here where I added up this and the difference left in the middle. What am I going to do over here that's similar to that? Difference of some sort. So this negative 1.11, all right, and this 0.8333. What question am I trying to answer? What does the question ask us?
What is the problem?
Yeah, so this is 19 miles. This is the z-score for 19 miles. This is the z-score for 26 miles. And I want the probability of being in between these two.
Right.
So you think I want to add this to this?
No.
No. What do I want to add?
Those two.
Yeah, I want to add, I want this stuff in the middle.
Middle.
Okay, so that's what I want. So I'm going to have to do some backwards type thinking when I look up the z-score for negative 1.11 and 0.83. But let's go ahead and do that. Let's look up 0.83 first.
0.7967.
Okay, so the area under the curve associated with this is 0.7967. So what does that mean?
79% are less than
Yes.
26 miles.
Yeah, so I think the easiest way to solve this one is what percentage are more?
So 79 minus, 100 minus 79.
21%?
All right.
Yep. I think that's the best way to look at this one.
20.33.
20.33%. Okay. Alright, now let's look up negative 1.11. And we're gonna have to do double duty here. So that's for 0.11, right?
And then
One more.
How you been at?
Alright, so you look up 1.1 and you get 0.865, right?
865, yes.
So that would mean there's like roughly 14.
13.35.
Yeah, so 13.35 if it were positive would be higher. But since it's negative, 13.35 are lower. Does that make sense? So this is 13.35%.
How did you get that?
Alright, question?
Yeah, where's that coming from?
Alright, so, what's your name?
Barbara.
Barbara. So Barbara, what did you start? You looked up 1.1.
Negative 1.11 is 0.8665.
Okay.
And what I did 100 minus 86.65, which gets me to 13.11.
Okay.
Okay. So the question is, what's the probability that any one particular person will have a commute between 19 and 26 miles? Sounds reasonable. Yeah, you just subtracted the difference, whatever was left out of 100. Yeah, 66 point what?
34.
Okay, I like it. No argument here. This area in between, 66.32. How do we like it? Okay. This is the key problem for tonight that we'll build on. The binomial stuff is warm up. Go ahead.
That's kind of an immediate question. Why wouldn't we add the outliers, the standard deviation negative 1.1 plus 0.833, and then subtract it by 100? Why wouldn't you do that?
Why wouldn't we, you mean like add this together and get like negative 0.3?
When we did that, when we added outliers, we subtracted it by 100, right?
Oh,
Why wouldn't
okay.
we do that here?
Yeah, so what we did the same thing. So we said 39% is on this side, and we said 1% is on this side. So we had 100 minus 39 minus 1.1 equals whatever we got. And we did the same thing over here. 13% is on this side, 20% is on this side. So 100 minus 13.35 minus 20.33 equals 66.32.
Yeah, but we did a little differently. So you're saying you have to have the z-score for 0.833 before you can actually do the math?
Yeah, that was my first question. Were you saying we just add these together and get like negative 0.3?
That's what I thought initially the first video. You're saying you need the actual z-score and then you can do it.
Yeah, because if you look, like the area changes here. So negative 0.11 is very specific about the area to the left of it. If we were to put these together, then we would be comparing a different sliver that would be way up here. If that makes sense. This is just good.
Can you go over how you got the 13.35%?
Yes. Okay, Barbara.
Yes.
All right, so the question is, how did you get the 13.35%?
So I added the two ends, 20.33 plus 13.
No, how did you get the 13.35?
Oh, so I did the.
So
the
first you get,
table.
first you get the z-score of negative 1.11.
Right.
Okay, excellent. And then what'd you do, Barbara?
I got the table, whatever I got for the table was 0.8665. So I made that into a percentage. I did 100 minus 86.65, and that came out to 13.35.
So she looked at, the Z table will tell you if it were positive 1.1, then that would mean, what is it, 86? 86.65?
Yeah.
If it were positive, then 86.65% of the data would be lower than that, which would leave this amount higher. And since it's negative, it's just the opposite. And this is the 13.35. Okay. All right. You bet. Okay. All right. So good. Let's see what else we have. I'm gonna get through this. I tell you, no matter what happens, we're not getting out before 9:30. So nobody get excited, right?
Okay.
So just know that. All right. So zero probability. All right, because I skipped around a little bit because I wanted to get some momentum going. Let's see. Distribution, we've got Z-scores on page 12, we're looking good. We did an example of the normal distribution. We did the male height example, we did another example. All right, now we're going to talk about, on the top of page 16, we're going to talk about frequency distributions, which you already know about. Then we're going to talk about measures of central tendency and measures of dispersion, which is all going to be easy stuff. All right. So take a look at the frequency distribution shapes on the bottom of page 16. Let's just look at the ones on the left. The top one is symmetrical, the middle one is positively skewed, and the bottom one is negatively skewed. All right, so almost all of the time in this class, with the exception of the next 10 minutes or so, all of the distributions we're going to be concerned with are symmetrical. Because if they're symmetrical, we can use the z-score to make important assumptions about them. Positively skewed, though, is something we want to be aware of, and we want to know how to interpret that. So positively skewed means that the numbers on the higher end have a greater probability, or they're more extreme. So in that tail or coin flip example, there'd be a higher percentage chance that you would get 19 or 20% or 20 heads than there would be that you would get the lower ones. Just means that the bigger numbers are more representative, or not more representative, the bigger numbers have a larger effect and they pull the average up. The negatively skewed is just the opposite. Let's take a look at a couple examples to put that in context. Again, I'm jumping around. Okay, all right, yeah, before I go to those couple examples, I want to look at the bottom of page 17, and I want to talk about the measures of central tendency. Mean, median, and mode. What is the mean? What is the median? Middle number. If you line all the numbers up, the one in the middle is the median. And what's the mode? Yeah, the most frequent one. Now, mean and median are sometimes used as the measure of central tendency because the mean can be affected by significant outliers. If you have one really, really rich person in your neighborhood, that person is going to pull the mean salary up in a way that's not going to be representative of what the neighborhood needs. The median number in a case like that may be more representative. All right, so now we're ready to get my two examples which show us symmetrical, positive, and negative skewed. Let's go to page 21. All right, suppose you have some income statistics for a town in New Jersey. You collect a bunch of data, you see that data, the mean income is 60,000 for each family, the median income is 60,000, and the mode is 60,000. That distribution is even, it's symmetrical, and it is a normal distribution. Mean, median, and mode are all the same. Now, let's take a look at an example on the next page, top 22. Suppose we have a different town where the mean income is 80K, median income is 60K, and the mode income is 60K. What's going on there?
Somebody with a higher income.
Yeah, there could be one person with a really high income who is pulling the mean up. There could also be a group of people with higher incomes who are affecting the mean. Now, the key here is it's not that there are more people who are in the upper income levels, it's just that the people who are in the upper income levels have more of an effect on the distribution. So it could be just one really rich person screwing everything up. Okay, how about the bottom of page 22, the opposite example. The mean is 45K, median is 60K, mode is also 60K.
There's one really poor person.
There could be one really poor person, yeah. There could be one, depending on how
That's so good.
it might be more likely that there's a group of really poor people, because if we turn back to bottom of page 21, there is one really poor person, right? There's at least one really poor person in that distribution too. And it's just that there's a group of them that are really, really poor.
So on the top one, on page 22, you have one really rich person pull it up, or you can't really have one.
Well, you could, because that person could be rich to infinity, right? But in terms of the one poor person, all you can be is 0.
Like your own money? You got it?
Yeah, yes, you could owe. Yeah, you could owe. That's a possibility. All right. I guess we could look at it that way. So there might in that bottom one there, and again the key here is it's wrong to say that there are more people who are poor, or there are more people who are making less than 60,000, because there are 50% of the people are making less than 60,000, 50% of the people are making more than 60,000. It's just the people who are making less than 60,000, they are more poor relative to the people who are rich. Make sense? Yes?
I understand what you're saying, but like you're talking people, and this just says like family, income.
Okay.
So really you're just looking at dollar units per residence.
You're right, I should have said family.
As far as a family or.
Yeah, I should have said family. You're absolutely right. Instead of saying people, I should have said family. So it could be one really rich family pulling the income up,
Right, yeah.
or a group of really poor families pulling the income down. Okay, everyone have that? Yes, sir. All right. All right, so standard deviation. Let's take a look at the top of page 20. We already talked a little bit about standard deviation. We said that really skinny bell curve has a small distribution, and the fatter bell curve has a wider distribution. And that can be represented with standard deviation. Definition for you, top of page 20. Standard deviation is approximately the average distance between the individual values in the data set and the data center. So the data center being the mean, what's the average distance from the mean? Here it's wide, here it's small. Or here it's large, here it's small. Is the best way to say that. So if you look at the bottom of page 20, you can see that little s is what we use when we're trying to calculate a sample standard deviation. And the sigma, the O with the little hat, is what we use when we're calculating the population standard deviation. And the population standard deviation is what we've been working with in our examples so far, and what we will often work with in class. It just means that if we have every member of the population, and we calculate the average distance of each member from the center, then we have the population standard deviation. If we just have a sample, all right, say you all are a sample of Mercy College students, and I were to ask you your grade point averages, all right, we'd have a sample mean for grade point average, and we would have a sample standard deviation of the 19 of you. The only difference in the calculation, you can see the sample mean. You see that it is divided by n minus 1 in that calculation, versus the population mean is divided by n. In capital N for every member of the population, small n for the sample size. So dividing by that n minus 1 means there's a smaller number than denominator, so it's a slightly bigger number. So for example, if I'm going to divide 9 divided by 3 equals 3, but 9 divided by 2 equals, what does it equal, 3.5 or something? 4? Oh, bigger, sorry, 4.5. Okay, so dividing by the smaller number gives us a slightly bigger number. The reason for that is if we just have a sample, we want to make the number a little bit bigger to account for possible error. When we're making statements like we're 99% confidence that the true mean is between this and this, we want a slightly bigger number if we only have a sample.
We're still subtracting x bar equals mean, right?
Yes, x bar is the sample mean,
Sample mean, but the mu is also equal to.
is the population mean.
Population, sample mean.
Yes, thank you. Good catch. As I'm trying to rush through this. The x bar is the sample mean, and the u is the population mean. Actually, I think we have that. Let's go back to top of page 18. Mean, as we all know, is the average of a set of data. And you can see x bar, if we just have a sample. Again, if you all are a sample of Mercy College students, I'm going to ask for your grade point, I'm going to average it all up, I'm going to divide by the total number, and then I'm going to have a sample mean, and that's x with a bar on the top of it. If I were to ask every single Mercy College student, then I were to add up all of their grade averages, divide by the total number, then I would have the population mean, which is notated with that u, sometimes called mu. Okay, so we've got median, we've got mode, we've got measures of this, and we're in the middle of a discussion about standard deviation, and we just did a quick side note for mean. Okay. So I have a little calculation at the top of page 21, which we could do really quickly, but I'm just going to leave that one alone. And yeah, I'm going to tell you that the takeaway is that the sample standard deviation is going to be a little bit bigger. We're going to divide by a smaller number so that we get a little bit more of a cushion. So you can see that example on the top of page 21. The population mean comes out to 1.7. The sample mean comes out to 2.08. Okay.
And your sample always has to be 20 or greater?
We'll talk about that later, but if your sample is 30 or greater, then you can make assumptions about normality. It doesn't have to be, but you can say, if I have a sample size of at least 30,
Okay.
then I can start using this type of stuff.
Okay,
and make these types of assumptions. My sample size is,
30 or greater.
yes, if it's 30 or greater, I can get into this good stuff. If it's less than 30, I can say, well, I mean, you know, I know that the normal distribution says this, but I have a small sample size, so I may not be able to rely on that.
Okay, so even when you're doing the n minus 1, so that your final answer is larger, that doesn't balance out, whether you do to the 20 or the 30.
You're right, it is, it does, it
It
balances out.
does.
Because
It
what
does balance
happens
out.
is,
Okay,
we don't use the z table, we use a t table,
okay.
which instead of looking like this, looks more like this. Wait a minute, no. Which just looks flatter. Instead of looking like this, it looks more like this. We have to account for the possibility of outliers,
Okay,
and we have to use a larger standard deviation. So if we were to do a problem like this number would be larger,
right. Mhm.
right? And we would come up with numbers which would just give us more of a cushion. When we say, all right, we're, you know, we have to have a larger, what we'll call confidence interval.
Okay, just because logically you know that if you've got too small a sample, it's not really gonna be reflective of a larger population.
It could be, the thing we account for is the possibility of an error. The possibility that we've got unlucky with the sample we chose.
Okay.
So we use a different distribution and we use a larger sample size. Great question,
Thank you.
great question. Okay, so let's reflect on what we did today. We learned combinations. I will tell you, because I feel bad that we just got so bogged down with that combination and binomial formula, that there is, I think, one combination question on the quiz.
How many questions are there this week?
5. There's one combination, so know that combination formula.
When do you post the quiz?
It's already
Post-
posted already.
Take it right.
And you get 1 hour, right?
Yes, yes.
Please live the combination.
Yeah, I think there's one combination question. There's also one binomial distribution question. So it'll be a question such as, you know, what's the chance of success? How many different times, how many different total number are there in this experiment, which would be our n? And what's the probability of getting exactly 4 successes out of 10 times?
Are they multiple choice or they're filled?
No, short answer.
And if you get it wrong the first time, that's it, you can't like continue trying.
Right. You just give one chance.
This is not kind of cat.
Not like
No, when you're doing, you put in an answer, and then you go to the next question, you realize that you made a mistake, you can't go back?
Go back.
Okay, once you submit it.
Once you hit submit,
then
you can't go back.
Then you're out of luck.
Yes.
Okay.
All right. Then the normal probability distribution, we became familiar with that. We learned how to calculate z-scores. And I'm sure there's at least one problem like this. So calculate the z-score, calculate the area under the curve, calculate the z-score, area under the curve. There'll be at least one problem like that. And there will also be, I think, one problem with that income. Like the mean is this much, the median is this much. What does that mean? You might say something like, well, maybe Donald Trump lives there, or maybe this is like a town where everyone is unemployed, except for the people who, are in this factor, or who do this or that. Alright, so I'm excited to have you all in class. Thank you so much for your attention.
Thank you.
Look forward to seeing you next week. Good. I'm glad you realize this was like, right, maybe next time I shouldn't spend so much time on that.
I took 5 to 7, so the prereq for this one, and 5 to 5.
Well.
For that.
Weakest in terms of determining what is
So you know how this came out for 796,000?
When I started this, okay, so I got waivers though, from 3 clients, so it wasn't that bad, yeah. Yeah, that was yeah, first time I'm taking graduate course this year, because I've had it on the mat, I had it in the mat and now I'm trying to go on one. Too far for me. I got to look at adoption and I'm quite free, because I'm right there, right around here, I'm like a mile.
How did I forget?
But with work, I was going back and forth, so it makes my heart cheap. So it's not bad.
Oh, that whole formula.
I have, after this class, I have one lesson. So I'm now working on defense. Thank God. Yeah. Yeah, that's what it is. I did 500 and this class I got, I had to have a really good class. So I already took the class to correction. So for me behind, that was like, when I went on my pre-audit, I don't remember taking that class. So I registered and had it throughout there. But it was great. I took some time off, so it took me a little bit. So, well, nice meeting you. Yes.
So you are already booked for the first time?
No.
It's the book.
We already have.
Alright, so, let's see, for number one, our following set of design is a whole body. So these are hours worked. The average video. So,
I'm undergrad too. I took some undergrad twice. First time I got a D, and I did it again. Professor.
So I didn't quite understand what you said, that's what I'm sitting at.
They sell out easy, those two.
Never will. No worries.
Yeah.
Okay, I gotta pick what I get. Okay, so you'll pay, and I'm gonna send it to you.
Oh, you haven't been there, right? To see your offices? Where did Beatrice go? I wanted to text her. I haven't been. I want to know what she's doing. But I like Beatrice. I'm tough. While I was in Brooklyn, she was no problem.
facilities, right?
And then these people.
How do you sort my blackboard? I never use it.
Oh, let's do it.
Yeah, I'll probably do a whole.
So,
Like I was telling
first of all,
Gail, it actually spells out.
so it's the same thing.
Oh, is it there?
You're gonna go.
The whole book, yeah, 1 through 7 is like half of it. Yeah, I only have half of it on me right now, so it's like for like. Yeah, that's what we're doing next.
You want me to bring help with that?
Yeah, for next week it's just that. So by tomorrow, I'll do 1 through 7 by tomorrow.
At all times.
Because I'm 1 through 7, but someone else is doing it.
Right now, it's
But 1 through 7 definitely like.
You know,
I don't know. Morning.
So you have one.
Okay, because then I'll go down to the
Oh,
college.
that's it?
I have to do it at home, I have to play with it.
I don't-
I can't.